Hey everyone, welcome back to more of our calculus work, and we're starting on chapter 10.5, and this is a chapter where we put together everything that we've learned about the convergence of a series. But before we can get there, we got to talk about that matter of what happens at the endpoints of the intervals of absolute convergence. We have kind of stated a few times that if our interval is from 1 to 6, then at 1 or at 6, our series could be conditionally convergent or it could be divergent. And we haven't actually examined what to do in those cases. So let's get started. We're going to actually examine those now. So here we have a kind of a summary of where we are right now. We take the limit using the ratio test, and based on what we see there could be three possibilities where, supposing L is less than 1, we get a convergent series. If L is greater than 1, then we have a divergent series. And if L is equal to 1, then no conclusion can be made. Now, these series were originally used to estimate the values of esoteric functions, so like, trig functions or exponential functions. And in order to use them, we have to make sure that those functions themselves converge, or the series that approximates the functions converge. So here's a quick review of the things we have. If we have a geometric series, then of course we can just test the ratio, and that really is the optimal situation. If it's not a geometric series, then we can quickly test for divergence just by checking if the general term tends toward 0. And if the general term does not tend toward 0, then our series is going to diverge. We also had the direct comparison test, and if you have two series, and if the bigger one converges and the smaller one converges, and if the smaller one diverges and the bigger one is going to diverge, you honestly get pretty limited use out of that, especially in the scope of AP Calculus, but it's still there for us if we need it. And then finally, we have the ratio test. But in the situations that we're going to be in, the ratio test is going to be kind of useless because we'll have used the ratio test. And if we use it again, we're just going to get something inconclusive. Hopefully we'll have time to kind of illustrate that to you. So basically what I'm saying is we need more tests. We need more ways to show whether or not a series is converging or diverging. So here's the first useful one that is coming. This is the second wave of convergence tests. And we have a series that looks like -1 to the n over root n plus 1. So if you look at that series, clearly the terms are going to tend toward 0. The numerator just has -1 to the n, and the denominator keeps on growing. So based on what we know about functions already, the general term is going to tend toward 0. But that doesn't necessarily mean we're going to have a series that converges. And then the next thing to notice is that the numerator of this series has that -1 to the n power. And that -1 to the n power is really, really, really something that you need to look out for, because that tells you that the series is going to alternate. It's going to have positive term followed by negative term followed by positive term followed by negative term. This takes us to what's known as the Leibniz Test. Leibniz Test for an alternating series. Sometimes students will call it the alternating series test, but Gottfried Wilhelm Leibniz is such a giant of mathematics that we might as well say his name. So this Leibniz test tells us that if we have a alternating series, if we look at just the terms without positive or negative, so the positive part of every term, then if that limit goes to 0, then the alternating series is going to converge. So basically, we're taking a look at the limit of the absolute value of each term. And if that absolute value of each term, if the limit goes to 0, then the series itself is going to go to 0. So this test is really, really similar to the nth term test, because in both of them, we're taking a limit of the terms of the sequence, or the series, I mean. But we have wildly different, maybe not wildly different, but we have different conclusions based on whether or not you're looking at a alternating series or if you're looking at a non-alternating series. So really be careful not to mix them up. And I find that the best way not to mix it up is to actually, state the theorem and what the theorem is. This is the Leibniz test. This is not the nth term test. So if you associate the name with it, then that'll help you differentiate between, the conclusions or the results of these two really similar tests. So be careful. We're going to try this out on this series over here, -1 to the n over root n plus 1. And let's see what we're supposed to do. So we start off by looking at the absolute value of every term and then finding the limit of the absolute value of every term. We talked about this in the previous lesson, but if we're taking an absolute value of a alternating series, then this -1 to the n power, whatever power it is, that -1 to the n power, the absolute value of that is just 1. So we're going to simplify this, and we don't need the absolute values anymore because the denominator is always positive. So this is equal to the limit of 1 over square root of n plus 1, and that doesn't need a whole lot of you don't need a whole lot of help here with that one. That the numerator stays the same, the denominator grows without bound, so this limit is just 0. So since the limit of the absolute value of each term is equal to 0, then the series converges by Leibniz test. Remember, Leibniz test is only for an alternating series. Do not try to use it or its results on a series that does not alternate. So as long as the exponent of -1, that alternating piece, as long as that contains both positive and negative values, no, that's not quite right. As long as it contains both odd and even values, the series is going to alternate. So it's a good idea also to cite the theorem so the reader, whoever's grading your AP test, is going to know that you're a studied individual. Somewhere down the line, that might just give you the benefit of the doubt and said, oh, this person, we have to decide, did they know what they were talking about? And maybe in the back of their head, they'll say, oh, well, they knew about the Leibniz test. Maybe they knew what they were talking about here. So a little bit of psychology here, but I strongly believe that you should be citing the Leibniz test in this case as well. So we're looking at this next series, which is the series of cosine of pi n over n. And we're supposed to decide if that converges. Okay, so does this series converge? So the hint is to write out the first 4 terms of the series. Let's go ahead and do that. Now when n is equal to 1, we get cosine of pi over 1. And then when n equals 2, we're going to get cosine of 2 pi over 2. When n is equal to 3, 3 pi over 3, cosine 3 pi over 3. Okay, that looks, and then cosine 4 pi over 4. Let's evaluate all those cosines and sines. And now things look really good. -1 over 1 plus 1/2 minus 1/3 plus 1 over 4. Now, you're going to, hopefully be able to write this out as a series that doesn't involve cosine. And the series that this is, well, it's -1 to the n over 1, -1 to the n over n. And I'm looking at this, and the only thing you really need to make sure is that the first term is negative. so that it alternates correctly. So when n equals 1, we've got -1 to the 1 power, which is negative. So yeah, this looks correct. We're going to start with a negative term, -1 over 1, then +1 over 2, then -1 over 3. Moreover, this is an alternating series, and I would definitely write the words alternating series on my paper. You want to look like you know what you're doing. The next thing is we're going to cite the test that is appropriate here, and it is the Leibniz Test. So we cite the Leibniz Test and we write down the start of this test, which is a limit as the absolute value of an goes to infinity. And we substitute our general term and we get the limit as n approaches infinity of -1 multiplied by 1 over n. The next thing to do is to simplify that absolute value, and that gives us the limit as n approaches infinity of 1 over n. Remember, the -1 to the n power, just like before, I think it was just up here, that goes to 1, so it's not necessary to put it in. And since there's no more negatives, we can take the general term, or a simplified general term, out of the absolute values now. And this limit's pretty easy. It's equal to 0. Now remember, we're not doing an nth term test, we're taking a Leibniz test. So when we get a 0 in the Leibniz test, the conclusion is converging. Therefore, the series converges. Pretty easy test, right? It's just one limit. Now moving on from the Leibniz test, we're going to move to another test which has everything to do with area, and it is the integral test. And so here's the idea. We're going to take the general term and we're going to turn it into a function of n, and then we're going to replace the function of n with x. Okay. And you can see that over here, we're taking the general term an, and we're turning it into a function of n, and then we're going to integrate f of x from n to infinity. N is just any old, any number, whatever is convenient, as long as you go to infinity. It doesn't matter where you start. And the idea is, if the infinite integral, which we studied a lot in chapter 9, if the infinite integral, the improper integral, converges, then the series is going to converge as well. We can illustrate the integral test by looking at this series over here. What about the series as n goes from 1 to infinity of 2 over n minus 10 squared? Does that converge? Actually, it does converge. It says to show that it converges. So to use the integral test, we're going to take the general term 2 over n minus 10 squared, and we're going to make it into a function, f of n, which is basically just a general term, 2 over n minus 10 squared. Then we're going to integrate the function from some arbitrary number. I'm choosing 15, and to infinity of f of x. And what we get is the integral from 15 to infinity of 2 over x minus 10 squared. Now this is an improper integral, so we're going to need to replace that upper limit with a dummy variable, which is usually b. And looking at strategies for integration here, probably what we're going to want to do is make a u substitution with that denominator. So let's do that u substitution with the denominator. We're going to say that u is x minus 10, and that means that du is the same thing as dx. So the integral from 15 to infinity of f of x is going to be the same thing as the limit as b goes to infinity of the integral from x equals 15 to x equals b of 2 u to the negative 2 power du. If I'm not making a total variable switch, then I like to remind myself that my limits are not in terms of u, but they are actually in terms of x. That way I don't accidentally substitute the wrong number in the wrong place. In any case, when you integrate 2 to the negative u, you get negative 2 to the 1 over u, and of course we're going from x equals 15 to x equals b. Now I'm going to substitute back for u, and remember u is x minus 10. So this becomes a limit as b goes to infinity of negative 2 over x minus 10. Substitute b in 15, and you get the limit as b approaches infinity of negative 2 b over b minus 10 plus 2 over 15 minus 10. Now as b goes to infinity, this first fraction is this limit to negative 2 over b minus 10. That's going to go to 0. And we know this because the denominator grows, but the numerator stays constant. So with all that simplified out then, what we get is 2 over 5, which is another way of saying the integral converges. And so since the integral converges, then the series that we made the integral out of is also going to converge. And that's a quick how to use the integral test. Okay, so with the integral test under our belt, we're going to switch gears again, and we're going to go to a new series test. But before we can get to that series test, we have to make a definition, and the definition is p-series. So a p-series is of the form 1 over n to the p power. Now this is a very strict definition. It has to be n to the p power and nothing else. Even 5 over n to the p power, that's not technically a p-series. So be very strict about what you call a p-series and what you don't call a p-series. For example, 1 over 2 plus n squared, that's not a p-series because of the plus 2. Now p could be any number, positive or negative, and the theorem that goes along with the p-series is a really conclusive theorem, and it is concerning p-series convergence. A p-series, will only converge if p is greater than 1. Not equal to 1, not less than 1, has to be greater than 1. Any other case, that p-series is going to diverge. So extremely concise, extremely conclusive. So this test is honestly a dream because it's, the results are immediate and easy to figure out. So just to show you, we've got over here this practice. Okay, for this first one, we have 1 over n squared. That is a p-series because the only thing involved, there's a 1 in the numerator and there's n to the second power on the denominator. So p is 2, and 2, of course, is greater than 1, which means that the p-series converges. Number 2, don't let this fool you. Even though it's a square root, it's still a 1/2 power. So this is 1 over n to the 1/2 power, which is a p-series where p is 1/2. So since p is 1/2, we know that this, 1/2 is less than 1, so that series has to diverge. Next one, we have 1 over the 5th root of n to the 8th power. So p here, that might be kind of difficult to see, but I think the power is the 8/5 power. So this is a p-series. P is 8/5, which is greater than 1. So that p-series converges. Anytime p is greater than 1, the p-series converges. And then just to kind of show you how versatile, I guess, this is, the cube root of n, that doesn't look like a p-series, but we could make the cube root of n 1 over n to the negative 1/3 power. So if the series can be written as 1 over n to the negative 1/3 power, then it's a p-series where p is equal to negative 1/3. Negative 1/3 is less than 1, or it's not greater than 1. So that p-series diverges. Very, very great things to look at. Love p-series. They really help us out a lot. And they're going to help us out even more when we get to our next part of this. which is a limit comparison test. Now, a p-series, because it's so strict, it only applies to a very limited number of series. So in order to get more use of it, we need to use p-series in conjunction with something called the limit comparison test, or the LCT for short. So if we have two positive series, A and B, and then we look at the ratio of their general terms, not the ratio test, the LCT test, and we see what the limit of those two, of that ratio is. If that ratio is somewhere between 0 and infinity, then both series are going to converge and diverge together. So if one converges, like the p-series converges, then the other series, which may or may not be a p-series, will also converge. If L is equal to 0 and the denominator series converges, then the numerator is going to converge also. And if the limit is infinity and the denominator series diverges, then the numerator series is going to diverge. The limit comparison test is what you're going to use for any series which is really close to a p-series, but is not actually a p-series. So that refers to mostly polynomial series, although it is possible to use the limit comparison test for other series. For you in AP Calculus, this usually means for any polynomial series that you come across. So let's see what we're going to do. Usage. That's going to be important. First, you're going to find the closest p-series to your unknown series. And I mean unknown as in, does this series converge or diverge? Usually you're going to just look at the highest ordered terms and look at the ratio of the highest ordered terms and use that for your p-series. Secondly, you're going to take that p-series, put it underneath the original series, your unknown series, and find the limit. If you show that the limit is any number between 0 and infinity, then whatever the p-series does, then your numerator series is going to do as well. Don't forget to cite the LCT, just like you want to cite the Leibniz test, just like you want to cite the ratio test, just like you want to cite the nth term test, just like you want to write the word geometric series. Write down, tell people that you know what you're talking about. So let's start off with 1 over 2n squared plus n plus 1. And we're going to try to find the closest p-series to this general term. So we'll start off with the exact same general term, and then the next thing you want to do is only look at the lead term. So I don't need to look at the plus n and the plus 1. If I had stuff in the numerator, I'd do this exact same thing to the numerator. Then, if I have any constants left, like that 2 in the denominator, I'm just going to get rid of it. At this point, our particular p-series is finished. This is 1 over n squared. But if you had, for example, n to the 3rd power over n to the 5th power, then you just simplify that to whatever it comes out to. And that's going to be your p-series. So let's take a look at our p-series. We've got 1 over n squared. We know that that p-series converges because p is equal to 2. And then we're going to take that p-series and we're going to put it as the denominator of our ratio of our limit comparison test. And then we're just going to simplify things. Okay, so that's equal to 1 over n squared plus n plus 1, 2n squared plus n plus 1, multiplied by n squared over 1. We're going to divide each part of this by n squared, which is the highest power of n. And that's going to simplify to 1/2. So, down to our conclusion, since the limit as n approaches infinity of a over b is the same thing as, and let's go ahead and simplify that, That's the same thing as the limit of n squared over 2n squared plus n plus 1. And we found that limit to be 1/2. And also, we compared it to b, and b was the same thing as b was 1 over n squared, which is a converging p-series. Well, that means that the series that we started off with also converges by the limit comparison test. So basically, the limit comparison test takes all of those series which are kind of like a p-series, and it allows us to find their limits, or to find whether or not they converge by comparison to a p-series. So basically, a p-series can be used for almost any other polynomial series. So let's go over our important ideas. We've got the Leibniz test for alternating series. Don't confuse it with the nth term test. We've got the integral test, which some of you might like, especially if you enjoy integrals. We've got the p-series, which by itself has limited use. But when the p-series is combined with the limit comparison test, then we have a really powerful set of rules to find convergence or divergence. Let's check our understanding with letter A here. We've got -1 to the n over 2 plus n. Now there's more than one way to do a lot of these, so don't feel like there's only one path to success here. There definitely isn't necessarily. And what I'm going to do here is I'm going to say, well, look at that. That is an alternating series. So I'm going to use the Leibniz test. Moving along with it, we know the limit of the absolute value of the general term is the limit as n approaches infinity of 1 over 2 plus n. Notice how I conveniently just chopped off the -1 to the n. And as n goes to infinity, the limit is going to be equal to 0, which is what we want for the Leibniz test. Because when you get a 0 in the Leibniz test, you've shown that the alternating series converges. Let's take a look at letter B. And letter B, we have 2n over n squared minus 8. That's not an alternating series, but the numerator and denominator are both polynomial parts. So since the numerator is a polynomial and the denominator is a polynomial, my idea immediately goes to the limit comparison test. So we're going to start off with looking at the general term of the sequence that's presented to us in the problem. And we're going to get rid of any extraneous terms, leaving only the highest powered term in the numerator and the denominator. That gives me 2n over n squared. Then I'm going to basically just get rid of any constant that's remaining. That gets me down to n over n squared. And then I'm going to reduce that down. That gives me a comparison p-series of 1 over n, which, by the way, is a diverging series. So now we're going to take a limit. So let's set up the LCT. So we've got the limit of a over b is equal to 2n over n squared minus 8, all over 1 over n. Next, we simplify, and then we evaluate this limit. I'm looking at that, and I think the correct thing to do here is to divide everything by the highest powered term, which is n squared. Great. So the only thing that's left with an n now is that 8 over n squared, and we know that 8 over n squared trends to 0. So the limit after everything is said and done is 2. 2 is a number between 0 and infinity. Since we compared our original series to a diverging series and we got a limit of 2, basically anything, then the limit that we started with is also going to diverge. Whatever the first limit does, which is the p-series, whichever the p-series does, that's also what the unknown series is going to do. So this is much better usage or look at the usage of the LCT test. Next, we're going to see if these series converge absolutely, conditionally, or diverge. So let's take a look at this, and we have -1 to the n plus 1, n squared over n squared plus 1. Well, I'm looking at that, and clearly it's an alternating series, but the n squared over n squared plus 1, that concerns me because that limit is 1. And we already know if the limit isn't equal to 0, the series is going to diverge. So this one looks pretty easy, the letter A. So the limit is not equal to 0. If you want to know what it actually is, I mean, the positive terms trend toward +1, and the negative terms trend toward -1. Basically, the limit doesn't exist because there is no one single value that the positive and negative terms agree on. In any case, that's not important. We just need to know that the limit is not equal to 0. So therefore, the series is going to diverge. Letter B comes with the hint to use the ratio test, so I guess let's use the ratio test. And I'm actually going to use a ratio test on the absolute value of this series because I have a feeling this is going to converge absolutely. So there's my absolute value, and we're going to use the ratio test now. So the limit of the ratio of the n plus 1th term over the nth term is going to be equal to the limit of the product n plus 1 over 2 to the n plus 1 multiplied by 2 to the n over n. So there are a couple of steps combined here. Hopefully that didn't go by too fast for you. We know how 2 to the n over 2 to the n plus 1 cancel out. That becomes 1/2. And then all we're left with in the limit is n plus 1 over n. And that limit should be pretty apparent to you. That limit, well, that should be 1. So we get a limit of 1/2. Now remember what the ratio test says. If the limit is less than 1, then the series is going to converge. We use the ratio test on the absolute value of the series. So the absolute value of the series converges. So if the absolute value of the series converges, then the series is said to converge absolutely. So there we have it with our first section here, section 10.5. We still haven't got to our power series yet, but we're building up to it. Next time we come back, we're going to look at the power series and how to find their interval of convergence finally. So have a good one. We'll see you next time.